Historically, a device known as an indicator was attached to research and experimental engines. This measured both the variations in cylinder pressure and the changes in piston position throughout the 4 strokes of the operating cycle. By means of a mechanically operated pen, the device plotted pressure against volume on what was known as an indicator diagram, or pressure-volume PV diagram, an example of which is shown here. Modern technology utilizes electronic sensing devices to obtain the same information. The indicator diagram is used to plot the variation in the pressure obtained. This determines the shape and the area enclosed by the graph. This area is representative of the work done on the gas and the power produced by the engine. This picture shows the indicator diagram opened out, so that the pressure areas under the curve can be more easily compared and measured. The area within the power column represents work done on the piston during the power stroke. The blue areas represent work done by the piston in compressing the charge during the compression stroke and exhausting the cylinder against back pressure in the exhaust stroke. Subtracting the sum of the blue coloured areas from the area within the power column leaves us with the red block. This is the average pressure on the piston during the working cycle. It's termed the indicated mean effective pressure, or IMEP. Having found the indicated mean effective pressure in the cylinder, it's now possible to calculate the indicated horsepower, or IHP, of the engine concerned, using the formula IHP equals P times L times A times N times E divided by 33,000, where P equals the indicated mean effective pressure in pounds per square inch, L equals the length of stroke measured in feet, A equals the area of the cylinder measured in square inches, N equals the number of cylinders, E equals effective working strokes per minute, or half the RPM, and 33,000, which is a constant that enables us to change foot-pounds of work per minute into horsepower, 1 horsepower being calculated by James Watt to be the equivalent of 33,000 foot-pounds per minute. The SI unit of power is the watt, or 1 joule per second. 1 horsepower equals 746 watts. Indicated horsepower is really only a theoretical concept. Power is required both to turn the crankshaft and move the piston. This power is called friction horsepower. To deduce the amount of power which remains to do useful work, for example to turn the propeller or drive a gearbox, we must subtract the friction horsepower from the indicated horsepower. What remains is called brake horsepower, or BHP. Heat energy is converted from the chemical energy in the fuel by mixing the fuel with the oxygen in the air induced into the engine and burning them together in the cylinder. This then is converted by the engine to mechanical power. The weight of fuel burnt in pounds for the brake horsepower released per hour is called the specific fuel consumption. A reduction in power for the same or greater weight of fuel burnt is defined as an increase in specific fuel consumption, whereas a reduction in fuel burnt for the same or more power is a decrease in specific fuel consumption. Specific fuel consumption is affected both by engine design and the way that the pilot operates the engine. Correct operation of the engine by the pilot is essential if the optimum performance figures are to be attained. Opening and closing the throttle smoothly and relatively slowly will go a long way to obtaining both good specific fuel consumption and long engine life. The term efficiency is used to mean the fraction of energy that is usefully transferred. We'll define the mechanical, thermal, and volumetric efficiency of the piston engine. The internal combustion engine converts the chemical energy in the fuel into heat energy, and then further converts it into mechanical energy. In the case of the piston engine, its mechanical efficiency can be defined as the brake horsepower divided by the indicated horsepower times 100. Typically, the mechanical efficiency of an internal combustion engine would be in the region of between 80 to 85%. The thermal efficiency of an engine can be defined as the ratio of the work done by the engine to the mechanical equivalent of the heat supplied in the fuel. For any heat engine, that can be shown as the heat converted into work divided by the heat energy available in the fuel times 100. An average value of the thermal efficiency of a gasoline aircraft piston engine would be in the region of 25 to 28%, whereas the thermal efficiency of a racing car engine could be as high as 30%. One way of improving the thermal efficiency of an engine design would be by increasing the compression ratio of that engine. More about compression ratio in a moment. The greater the weight of mixture of air and fuel that the engine can draw into the cylinder on the induction stroke, the greater will be the power output of that engine. The volumetric efficiency of an engine is the ratio of the weight of gas induced into the cylinder on the induction stroke to the weight of gas which would fill the cylinder at standard temperatures and pressures, expressed as a percentage. For an internal combustion engine, this can be shown as volumetric efficiency equals the weight of mixture actually induced into the cylinder divided by the weight of mixture which would fill the cylinder at standard temperatures and pressures times 100. A normally aspirated aircraft engine, that is, an aircraft engine that is not supercharged or turbocharged, will not be able to induce sufficient mixture into the cylinder to fill it completely. In fact, this type of engine would only have a volumetric efficiency of about 80%. Volumetric efficiency is affected by the size of the intake manifold, the carburetor throat, valve timing, and cylinder head design. All of these items affect how much mixture will flow into the cylinder. In order to define the compression ratio, it's necessary that we define three other terms first. The first of these is the total volume. The total volume is the volume that remains above the piston when the crankshaft is at bottom dead center. Swept volume is the volume displaced by the piston in a single stroke. Finally, clearance volume is the volume that remains above the piston when the crankshaft is at top dead center. The compression ratio of a piston engine can be defined as the ratio of the volume in the cylinder with the piston at the bottom of its stroke to the volume remaining with the piston at the top of its stroke. Expressed as a formula, this would be compression ratio equals the total volume divided by the clearance volume. We stated earlier that one way of improving the thermal efficiency of an engine design would be to increase the compression ratio. The aircraft piston engine is made up of a number of component parts. We'll now describe the most important of these in some detail. The crankcase is usually made in two halves to make installation and removal of the crankshaft easier. It houses the main bearings for the crankshaft, supports the cylinders, and provides mounting faces and spigots for the attachment of the other main engine casings. Generally made of light alloy, the crankcase, the sump, and the accessory housing together form a sealed chamber for the lubricating oil, and are provided with a means of attaching the engine to its mounting frame in the aircraft. The crankshaft converts the reciprocating or linear motion of the pistons into rotary motion, and transmits torque to the propeller, and also provides the drive for accessories. The offset crank throw determines the piston stroke. The journals, the main part of the shaft, are supported by the main bearings in the crankcase. The pistons are attached by the connecting rods to the crank pin. The crankshaft will normally have as many crank throws as there are pistons. That is, 4 throws for a 4-cylinder engine. Passages are drilled through the crankshaft which communicate with oilways in the crankcase. These transfer the lubricating oil onto the bearing surfaces. Plain bearings are used to enable the high reciprocating loads to be carried in simple 4- and 6-cylinder engines, although in larger engines roller or ball bearings are sometimes utilized. The crankshaft must be accurately balanced to minimize vibration. This picture shows a machine which is designed to enable crankshaft balancing to be carried out. In the case of a radial engine, several pistons may be connected to a single throw, as is shown here, and a horizontally opposed engine may have two pistons connected to one crank pin. The repeated applications of force to which the crankshaft is subjected may set up oscillations as the shaft recovers its original shape between power impulses. At certain speeds, the impulses may coincide with the natural vibration period of the shaft, and give very rough running, even in an engine mechanically balanced. For these reasons, the crankshaft should be as short as possible, and supported by the optimum number of main bearings. Inevitably, engines are built to a compromised specification, and thus most engines have an RPM range which is prohibited for prolonged use to protect them from unnecessary vibration. This prohibited range is sometimes indicated by a yellow or amber arc on the RPM indicator. We stated earlier that we could improve the power output of an engine and make it run more smoothly by increasing the number of cylinders incorporated into the engine. This is because the more cylinders there are, the greater the number of power strokes in 720 degrees of crankshaft rotation. The greater the number of cylinders, the smaller is the interval between power strokes. This interval is called the firing interval. 4 cylinders are generally regarded as the minimum number to give reasonable firing interval. The crankshaft and cylinder arrangement will also determine the order in which the cylinders fire. This is called the firing order of the engine. Typically, 4-cylinder inline aircraft engines have a firing order of 1, 3, 4, 2, although the Lycoming 4-cylinder horizontally opposed engine has a firing order of 1, 3, 2, 4. The connecting rods transmit the forces of combustion to the crankshaft and assist in the conversion of the linear motion of the pistons into the rotary motion of the crankshaft. A connecting rod is usually made of H-section high-tensile steel, which combines lightness with the strength necessary to withstand both the compressive and the tensile loads which are imposed as the piston changes direction at the end of each stroke. The connecting rod is joined to the crank pin of the crankshaft by a large white metal bearing situated at the big end of the rod. The white metal bearing is made up in 2 halves, which are called a shell bearing. The connecting rod is joined to the gudgeon pin in the piston by a smaller bearing at the little or small end. Generally made of aluminium alloy, the piston forms a sliding plug in the cylinder and transmits the force of the expanding gases via the connecting rod to the crankshaft. Bosses are formed to house the gudgeon pin, which connects the piston to the small end of the connecting rod. Circumferential grooves are machined in the piston to accommodate the piston rings. Piston rings provide the means of preventing combustion pressure leakage past the piston into the crankcase, and oil leakage into the combustion chamber. A number of piston rings can be fitted to a piston. Their arrangement will vary from engine to engine, but will be similar to that shown here. The compression rings prevent gas leakage into the crankcase. They are fitted into grooves cut into the upper portion of the piston. Gas passing down between the piston and the cylinder wall forces a compression ring down into its groove and outwards against the cylinder wall. A small amount of gas will pass the top ring, so a second and sometimes a third compression ring is fitted. The oil control ring prevents excess oil passing into the combustion chamber, and also spreads the oil evenly around the cylinder bore. Scraper rings are designed so that the bearing face is reduced in area and the bearing pressure consequently increased. The piston rings are generally made of a special grade of cast iron and are sprung against the cylinder walls. Cast iron has the ability to retain its elasticity when heated. It also has self-lubricating qualities due to the graphitic content of the metal. This is desirable because during the power stroke, the walls of the cylinder are exposed to the hot combustion gases, and the thin film of oil is burned away. Piston rings which are either worn or stuck in their grooves will cause excessive blue smoke, which is burnt oil, to be ejected from the exhaust pipe.